I was asked to on molecular replacement. Is that not? Okay, is that all right? Or I can try again. Okay? Yeah, good. Okay. So I've taken the liberty of borrowing extensively from other people's presentations to put together something which is a very basic introduction to the things you need to think about in molecular replacement. And I suggest all the PIs leave the room now because it's probably an insult to what you know already. But and I should apologise. Keith has told me that no one will be able to listen because the fonts are different as I go from one slide to another. But just be tolerant. When you borrow too much, you do get a lot of different fonts. Okay, so that's the first thing. Oh, well, why didn't that work? Oops. Do I have to press that? Yes. Oops. Now, why doesn't that work? It does. Just a basic thing, this is taken from somebody's textbook. We want to go from a crystal to diffraction to a model. That's fair enough, and that's exactly... And that's been true as long as there's been crystallography used as a tool for chemistry and biology. The next thing I think that you all ought to well, I'm really talking to students now, I'm sure other people know this. We ought to think about why we're solving the structure. I think for us as structural biologists, because we want to answer some question about how this thing functions within a much more complicated system than just a single molecule. And so it's true, it's certainly in New York, and I think it's probably true in most places, that people start from a sort of more biological perspective, about they have a reason for trying to solve a structure, and crystallography is a tool that allows you to get to this understanding. So that's changed from when I was first in the field, when the whole thing was we didn't understand the crystallography. So now the crystallography has become more basic, but it's still worth, I think, thinking about some of the crystallographic tools and having some understanding of them. And of course, people are going to discuss refinement. Our data is going to be imperfect. Our data is from a molecule we think is trapped in a single conformation. It isn't. So we're going to have to consider refinement before we get a decent answer. Now, I broke this down into several points that I thought we needed to think about. We need to understand the biochemistry. That means you have to read the papers. You're going to need, if you're going to use crystallography, you're going to need a crystal and be able to measure some information about that crystal and to understand something of the properties of crystals. And for those, it's essential before you can solve a structure, you have to have some phasing, some start in the phasing. It can either be done experimentally or by direct methods, or in this meeting we're going to be discussing fitting a known model and using that as our starting set to get some phases. And then, of course, we're going to need to refine it. So what do we have to think about to do this procedure? The first thing, of course, is to select a model. And there's going to be a lot of talks later on about how to select the best model and what to do. But that's one of the most crucial parts of getting a decent molecular replacement, is to have made some intelligent choices of what you're going to use as your starting model. It's certainly going to help you when things get difficult if you understand some of the basic crystallography, and I'm just going to touch on that, but as I say, probably, I hope maybe people know it, maybe they don't. Your crystal has to diffract, of course, and that's another problem which is done. And then I'm going to touch on the technical issues underneath molecular replacement, but there's going to be a lot of talks about that later in the meeting, so I won't do that. And I've been asked to talk a bit about the history, for what it's worth. So selecting a model, we need to do, how are we going to do that? What we usually know, and probably all we know to begin with, is the sequence. And we've got, well, when I started, there were very few bioinformatical informatic tools to use that sequence. But now there's a whole wealth of tools which allow us to search the known structures to see if we can find any match between our sequence and something that's been deposited already. When you get that match, there's several things you can deduce. One is, say you find 20 matches, do they all agree? Is there a difference between them? But you can spend time looking at those models and thinking. As I say, timing, that's when you think, because waiting for a crystal to grow is really, really boring. So it's worth doing that. Things to consider is, are there different domains? Do the models form an oligomer, and is that the biologically important thing? So that's a point where you can spend a lot of time happily in front of graphics terminals doing this sort of work. And I've just given a couple of examples. One is S100, which is a calcium-binding protein that's only 100 residues, not a very big thing. If you search at the PDB, you find quite a lot of good models. In fact, I've listed 4, which all have exactly the same sequence and exactly the same sequence ID, 46%. So download them. In fact, if you use PISA, it will tell you that, that the 1RIJ forms dimers, that in this particular crystal that's available, there were 8 different dimers, but the dimer formation seems to be a fundamental part of the thing. And the references there, this was done a long time ago. And the author of the first paper, Olga Morris, supplied me with this. It's interesting because it is calcium binding, and when you get calcium, when the calcium binds, there's a dramatic change in 2 of the domains. You can see the outer pair of helices have turned right out. And so you needed to know before you started your search whether or not this S100 model was a calcium binding form or not. But it was very obvious from aligning the structures that there was a big difference between the 2 classifications of models. And the next thing, which is, again, I haven't got a beautiful slide as the other one. That one, previous one, was made by CCP4MG. When you looked at 2 of the models, 1RIJ and 1XK4, the domain, the top part is the first part of the dimer, the bottom part's the second, and that the actual dimer interface has changed quite drastically between one model and the other. And in fact, it was 1RIJ that overlapped much more closely with S100. But these are things that is worth knowing, that you're going to have a different dimer interface, possibly. So that was the example of S100. And I say, I've always put in a plug for CCP4MG with Mr. Bump. It does a sequence search, and then you have the visual ability to look at all your models. And when you look at those models, you might decide what you want to select. Do you want to just take a single example? Do you want to take an ensemble? Do you want to trim that ensemble? Do you want a single domain, separate domains? Or, people later are going to talk about the fact that you can just use, if you've got good enough data, a single accurate fragment. And this is something that Hugh Jenkins prepared. The blue model is the actual solution. You can see the blue model has its completeness on this side, RMSD on the bottom. My numbers have got up, but on this side it's 0, identical to the model. On the other side, it's a difference of 2 angstroms. If you took the whole model, well, it's easy. If you start aligning things, you find a whole lot of matches, and you can see that they overlap roughly, but not very closely. You can extract a single one from it. So it's just goodness me, Hugh, you did a lot. Or you can take a little bit, or you can take. Oh, sorry, I thought this all came up as one single slide. Or you can just take one helix, and there's advantages in if you've got high resolution data. The single helix can work beautifully. But this sort of thing, this examination of your different models, is something that is worth doing and worth thinking about before you start the process of molecular placement. And the other example I was going to talk about was insulin, because after all, it was the first structure I was involved in. But insulin, actually, in in your islets of Langerhans forms hexamers. If you look at that electron microscope, you can see hexamers, and they do pack exactly like they packed in the crystal structure. But the crystal structure, the hexamer, is made up of 6 chemically identical chains, which is, and so you either find a monomer, a dimer, a hexamer. And so these are questions. And the crystal symmetry is involved in this, in which form you're going to generate as well. So what can we deduce? Well, we can deduce that that the mixture of symmetry from the biological molecule and the crystal symmetry can make a terrible, terrible headache. You can, it would be nice if the hexamer just floated around and crystallized with one in an asymmetric unit. It often doesn't. You often have to consider the fact that the biological molecule is going to be generated by crystal contacts and by crystal symmetry. So, what do we need to know about crystallography? Well, first thing we need to know is we need to really have some understanding of symmetry. And people find symmetry a pain in the neck, but it's quite important. Then, as I say, there's certain equations that we need to think about, which I'll go into in a minute. Just the basis of symmetry. If you're going to have a crystal, you can only have just a unit cell repeat, or you can have a 2-fold axis, a 3-fold axis, 4-fold axis, or a 6-fold axis, and you can prove mathematically, if you will find in a book, that those are the only symmetry operators which will generate an array with straight edges, and crystals have to have straight edges. So, and these symmetry operators can also be involved with translations, so that we can have the 3-fold can be expressed as an exact 3-fold or as a screw axis, a 4-fold, and so on. So let me just emphasize to students, the International Tables is still a wonderful resource, and for goodness sake, at least know where it is, so you can go and find it. I guess most laboratories still have a battered copy somewhere, and it does help you understand when the crystallography gets messy, I find. That's a page for P2121, but know where it is, know what it looks like. And in P2121, there'll be 4 molecules arranged by the symmetry operators x, y, z, a half plus x, a half minus y, minus z, and so on. And I should emphasize, just going back to the insulin example, over the years we've solved many, many insulin structures, and they're in this. I just collected the range of space groups that they're in. You may notice that a lot of them have 3-fold axes, but it's a pain in the neck sort of sorting out what you're going to find. The interaction in the first one we did, which was the R3, there was a dimer in the asymmetric unit, and the 3-fold axis generated the hexamer. It existed in P321, which has one 3-fold axis in the middle, and then another molecule sitting out in space somewhere, but with symmetry generated by the operators. They're in the cubic insulin, which is the one that everybody uses as their test data, the bottom one, the 3-fold axis runs diagonally across the unit cell. So then I'm sorry to put this up. I know people hate equations, but all these equations are available. In fact, even in CCP4, there's a thing called basic maths for crystallography. But if we know where the atoms are relative to some origin, we can calculate a structure factor. And that's that way. I haven't got a pointer, but anyway, it doesn't matter. And we will find, when we've calculated that structure factor, it will have a certain magnitude. That magnitude should match the magnitude of the structure we'd observed. Okay? If we move all the atoms by just shift them all by x0, y0, z0, calculate the structure factor again, we'll find that the magnitude is exactly the same and the phase has changed. You don't have to, but that's something that's important, because we have this business that when we've done molecular replacement, we can use the magnitudes to check that matches our observed data, but the phases can have a variety of reasons, of positions. It's important when you run the same molecular replacement in 2 different forms, you probably will find a solution which is on a different origin. So you need to be aware that this can happen. Yeah, just another bit of maths which I'll put in the document. Of course, in my the previous equation, I just assumed all the atoms were at x1, x2, x1, y1, x2, y2, z2, and so on. But in fact, often within our crystal, they're related by a symmetry operator, so that half of them we only need to consider one half, and then we can generate the position of the other halves by applying the appropriate symmetry. The structure vector then becomes a sum over thing. And the symmetry operators are listed relative to an origin. And just saying the same things I said before, if we went back to P21, the origin could be in the top left-hand corner, it could be in the middle of the thing. So we'll get a solution which was relative to an arbitrarily chosen origin. Problem to consider. And so to say the same thing again already, all the scoring things which decide whether you've solved your molecular replacement or not can only look at the amplitude, the magnitude of your structure factor, and so we have to consider origins. Now, the second equation, which I guess you all know, is the electron density map. If we know the phase if we've calculated a phase, we can calculate an electron density map on a grid, and that where there is an atom, there'll be a high peak in the contour map. Where there's not an atom, that should be 0. That's important because everything we do in the way of rebuilding and bootstrapping depends on the difference Fourier. And the difference Fourier is one of the great miracles, I think, of crystallography. We've collected observations. Every observation has information about every single atom that was repeated within the crystal lattice. And even if we only have partial phases, poor phases based on a fraction of the model, when we calculate this map, we'll get some indication of where the other atoms should be. And you can prove this mathematically, that the height of the missing atoms is a function of the ratio of the known atoms that we've included in the phasing to the ones that are missing. And there's various ways of enhancing that map and weighting it better, but it means we can bootstrap. We get a partial model and we can start seeing something in the map which allows us to extend our model. And these are just examples of different difference maps. There's a very important parameter at the top, which is that K, which is how we're going to scale our observed data against the amplitudes we've calculated. I won't go into how we choose K, it's quite tricky, but ideally we'd see a maximum in our map where something is missing, a minimum where we've done something wrong, and that's an example where you can see blobs for the hydrogen atoms in that small molecule structure. And this is an example from Paul Emsley's website, which I think most of us could correct that tryptophan and work out that that there is green electron density where the atoms should be and red electron density where they've been built wrongly. And somebody's put a water in which shouldn't have been there. So we're going to use this bootstrapping technique. And the fourth equation that we need to know about is the Patterson. And again, you can work out why Patterson is a good thing, but you can calculate a Patterson without any phase information and simply summing using the intensity, which is the function of the FH by FH star, so the phases cancel out. And you'll find peaks in that Patterson map which represent the difference, the vector difference between all pairs of atoms. And that the height of that will be a function of the scattering power of each atom. So if you have a heavy atom, it will show up very much more strongly than the vector between two carbon atoms. So that's an equation that we use, of course, all the time. Just important properties. Okay, you can calculate it without the phases. It's a vector map of the structure, so it's centrosymmetric. So if you've got a vector from atom 1 to atom 2, you'll also have the vector from 2 to 1. You can bootstrap it. And just a warning, which is no longer true, but it used to be so true 25 years ago. If your data was incomplete, your Patterson is often very distorted. And it's particularly bad if you've lost the low-resolution data. That's important. I don't think that happens now, but for goodness sake, when you do your data processing, just check that it hasn't happened. Then I wanted to put in this example because it is historical. This, as you know, Dorothy Hodgkin solved B12 in the 1950s, which was at the time an amazing structure because it was 100 atoms, but the crystal contained a cobalt. So they were able to find the cobalt from the Patterson. As you can see, there's one big peak and they could position the cobalt atom. And then they slowly bootstrapped their way up in a way that we're still doing in molecular replacement when you say fit only a helix. The cobalt was, I think, something like 16% of the scattering matter. So in the first map, there was not much density, but they were able to pick out, they knew the chemistry as well, they were able to pick out that ring there and add a few more atoms to the thing. Second map, they'd now had 8 atoms, better map next time 17, and in the end, by this bootstrapping technique, they got to the complete structure. And it's still very much what we do, but except now we do it automatically. We don't wait for months to get a single map calculated and so on. To recap, the structure factor, if you've got a decent model and you've positioned it properly, there'll be some agreement between the measured and calculated. There'll be some truth in the phases, even from partial structure. And maps with those phases will show new features. And in fact, there's a nod there. That we've got to get, but we still have to get phases, so how are we going to do it? Keith says I didn't give him these things, but there we are. We haven't got enough data to use direct methods. We're not going to discuss experimental phasing today, but we're going to discuss molecular placement where we position the structure, approximate starting phases, and bootstrap. So what can we do next? If you go back to my things, we obviously have to have a diffracting crystal so we can measure something. And I can't emphasize enough how important it is to spend some time, once you've got a crystal, once you've got some experimental data, think about it, because this is another point where thinking is really, really good. How complete is the data? Was there severe irradiation damage? Have you lost all the low-resolution data because you've smashed the crystal before? Are the intensity statistics sensible? You know, has the Wilson plot got a huge bumps in it where it should be linear? Is the data twinned, etc., etc.? So spend some time on that. And I should say, the report that's now in part of I2 is, I think, an excellent place to start. Read it all and think about it. But anyway, say you've got decent data. What do we know? Well, remember that you don't know the space group, although, where's Phil? Although it says you know the space group, you don't know the space group at the end of the data processing. You know the point group, and that will tell you that you had 2-fold symmetry or 3-fold symmetry or whatever. You can work out the volume of the asymmetric unit for your crystal, and if you know what you expected to crystallize, that means you've got some idea of how many molecules you're expecting to have to look for. And that's the technique called Matthews coefficient. And this is just a warning about Matthews coefficient. If you go through the PDB and look at all the structures, on average, about 50% of each crystal is protein or macromolecular. About 50% is solvent or empty space. But there are exceptions, and so when you estimate the number of molecules, these are 2 exceptions that exist. The one at the top, is, as you can see, is sort of a lace, and it was 90% solvent, crystal structure. The one at the bottom is incredibly densely packed, and there's only 26% solvent. So again, remember that we don't know the space group, we have some intelligent guesses. We don't know the number of molecules, we have some intelligent guesses. So, yeah. What more can we do? Well, we can calculate a native Patterson just using our observed data. And that's worth doing. I'm sorry, this is terribly sort of lectury. Because from that Patterson, you can decide whether you've got what is called a non-crystallographic translation. And this is a slide stolen from Ellie, as many of my slides are. If you look at the top, she's got 4 atoms, which are in exactly same orientation as a second molecule, which is the 4 atoms on the right. And if you calculate that Patterson, the vector from atom 1 to atom 1A, 2 to 2A, 3 to 3A, 4 to 4A, and so on, will all be exactly the same length in exactly the same direction. So when you look at that Patterson, you're going to get a lot of vectors are going to overlap. And you will see in the Patterson a great big peak, which tells you that these 2 molecules are probably in the same orientation but related by a translation. And it can make all sorts of problems for you, because very often that translation, say, might be XY a quarter. And for reasons I won't go into, if you have a translation of XY a quarter, you will have absences along your C-axis, which might make you believe that your Patterson was that your space group was a 4-1 or a 4-2, where in fact it's not at all. It's just a result of the crystallographic translation. So there's problems, and it also, as I'm sure somebody from Randy's group will be talking about, it introduces correlations into the structure factor analyses that we've used to decide whether our data was good or not. So, we need to know it's there. We don't know yet what to do about it, but we need to know it's there. And then I'll come back to this later, but there's another thing you can deduce from the native Patterson, and that is, even if they're not related by translation, we can perhaps work out how different copies of the molecule are related relative to each other. And, we might find that we've got a GRO-EL with a 7-membered ring of molecules or something. But I'll talk about the self-rotation in a bit. So at last, here's what are we actually going to do? We've got to position the molecule in the different space groups, and that will be up to a 6-parameter search. We've got to check whether the structure factors agree, and there's all sorts of ways of checking this. The traditional old-fashioned one was the R factor or the correlation coefficient. People will talk about better scoring algorithms. And then we've got to look at the maps and see, does it look right, and can we improve the model that we've started with? So this is an aside. Please, if you find that your new crystal is almost identical to something that's a model that's already there, it's in the same cell dimensions, the same space group, don't do molecular replacement. Just take your model and start refining it, because otherwise you'll find it's on a different origin and you'll give yourself a terrible headache later on. So, so if it's in the same space group, this is not molecular, it's just a refinement problem. But this was Early's slide again. Early. We want to go from that orientation of a model into this orientation of the thing in the new space group. So, are we going to do? Oops. So we've got to find. First of all, we break this up into 2 parts. This is all technical. We're going to first of all find out how to rotate the model so it's lying in much the same space way, and then translate it into the new unit cell so it's positioned properly relative to the symmetry operators of the new unit cell. Okay. So that's what we do. Now, just going back to the rotation problem, this is mathematical and it's a pain in the neck. When you use rotation matrix, you always define it relative to some orthogonal axes. And of course, the trouble is that the crystal doesn't necessarily have orthogonal axes. So you do need to understand, and I can warn you that there's software out there that uses different conventions, which is a pain in the neck, but there you are. So we need to get a rotation matrix relative to orthogonal axes, and it's going to be a function of 3 angles. It doesn't really matter whether we express them in Euler or polar or what convention we use. But just the deviation about rotation matrices, they have to have the property that their determinant equals 1. Well, the inverse is identical to the transpose. And most of our software uses the orthogonalization convention that X is parallel to A, Z is parallel to A cross B, and therefore Y will lie in the AB plane. I won't prove why that's true, but that's a fact. And here's a picture, which is I tried to draw. We have a unit cell with different length axes and different angles, and we usually define the X ortho along the A-axis, the Z ortho perpendicular to AB and the y ortho in the AB plane. So it doesn't matter very much, but there you are. First of all, so that's a rotation matrix. We've got to reorient the thing so it's in the same relative orientation to those orthogonal axes. And then we have the problem of finding the translation vector. So why do we need to worry? You know, I showed you that if we move things relative to the origin, the structure factor stayed the same. In a P1 cell, we don't consider symmetry, but as soon as we consider symmetry operators and we want to fix the symmetry operator properly, the translation will be an important parameter in calculating it. So yes, that's the same thing again. We want to know where to translate it relative to a symmetry origin. Yes. I'm just putting all this up at once because this again was taken from early. I'm sorry, early. Why don't we just check the parameters? Why don't we just move the thing around through the unit cell? Well, the fact is that, you know, if you consider all possible translations, all possible parameters, you finish up with a huge number of things to test. And even with modern computers, that's fast. That would have taken a long time. As he says, sorry, why is that happening? Can we check the agreement of FOBs just after the rotation? In other words, we're just saying we've solved this structure in P1 and we've only got one of the end symmetry molecules. Well, of course we can, but we won't get such a good score as if we generated all the symmetry equivalents. So you get the tests that we do for correctness improve the more of the crystal contents you have described. Yeah, well, that's just the same thing. Now I'm just going to do a little bit about, this is all written up in the literature. There's an excellent web page at Cambridge showing, describing this methodology, but just to go through it, I'm only going to discuss using a Patterson method, which was the workhorse of the original Merkur Patterson software. When we're doing the rotation function, we look at the Patterson between which our model would generate against the Patterson we calculate for the new data we've collected over a spherical volume is centered at the origin. And then we're going to do the translation function later that. And the great advantage of working in a spherical volume is that we can use spherical harmonics to search it, and for mathematical reasons, this means that we can use fast Fourier transforms. It becomes quick. So we can look for many orientations very quickly, and the rotation function doesn't take, 15 days to solve. So, so these figures were something that Airlie prepared in the middle of the night in Cuba. What we do is we take our model, we put it in a big box. For convenience, we choose orthogonal axes, and then the Patterson peaks, the molecules will exist at different origins, and we've got clusters of coordinates. And then next, so that when we look at the Patterson from that model, the vectors are fairly well separated. If we draw a sphere around the origin, we've got most of the vectors in that box are from a single molecule. This isn't so true when you've got a very elongated molecule or something complicated, but in this, for a standard case, this works. But then we've got to look at the Patterson for the crystal, the same structure in the crystal, and of course there, the thing isn't in a big box. They won't be widely separated. So when we draw all the possible orientations, they're going to overlap quite badly, and the Patterson is not going to be quite so clear as it was for the box, but when we overlap them, we should still get a signal from our nice, clean model Patterson and from the rather more messy crystal Patterson. And indeed, you get a reasonable thing. So there's as I say, if you actually look at a Patterson from a real crystal, it's absolutely uninterpretable. But in there is a signal. There's going to be a similar pattern as the one we got from our model. So that's that. And traditionally, it was done by this Patterson overlap function, which was integrated over a sphere. or a shell of a sphere, not the origin. The translation function is the attempt to find where that molecule, we've now got in the right orientation, where does it sit relative to a symmetry operator. So if you see here, there's a symmetry operator in the middle of the picture. Say we put the molecule down low and up high, you can see all the cross vectors from one symmetry equivalent to the other are going in one direction. If we move it up, then the vectors between symmetry-related pairs are going to move differently. So we should, in the translation function, be able to search and identify a different position for that. And indeed, that's what we do. We overlap the Pattersons, and I won't go through this, we can do this a lot, applying each symmetry operator in turn. We get a solution which fits for all the symmetry operators, and we can get a shift. We've still got the problem of the alternate origin. And another scoring function. These are going to be discussed at length, I'm sure, later on. Maybe it's better to do a correlation function between the calculated and the observed data than an R factor. In fact, it probably always is. I want to just go back and touch on the, I've no idea what the time is, touch on the business when we, pardon? Okay. When we touch on the business of when we have more than one molecule in the asymmetric unit, non-crystallographic self-symmetry, we can do a self-rotation, as they call it. Two molecules now related by non-crystallographic symmetry. The vector pattern will have twofold symmetry in it. It's complicated because it gets messed up with crystal symmetry interacting with model symmetry. It can be very misleading if you've got high symmetry in your space group, but it can help. And I've got two examples. One is a thing done where we had five-fold symmetry, and in fact, we can't see, but the bottom panel is the rotation of 72 degrees, and there was a huge peak. The molecule was forming five-fold symmetry, and knowing about it was valuable. This was the S100 one, which did indeed have a dimer, and somewhere over there, right on the right, is an arrow to the peak from the self-rotation, which told you where the dimer lay. But in fact, how could you, it's just a mess. It was not a useful piece of information. And in fact, the S100 was solved quite easily by searching first for one copy of the molecule and then for a second. Just a warning that when you get such a solution for molecular placement, they're usually not necessarily paired as a dimer. You had to move the gold molecule to its symmetry equivalent position before you actually had created the biological dimer. PISA, again, will do that for you and tell you the answer. But it's worth, you need to think, even when you've got your molecular placement solution, whether you have got the biological oligomer. Yes, as I say, it's can be very confusing. If you're looking for five molecules and they don't form a ring like that you expect them to, it looks a mess. Symmetry holds everything together. It's great when you see it. And I must warn you, all of you who go to workshops, we choose tutorial examples which are far too easy. So they're not, you can find yourself facing up to things which are much more complicated than our tutorials. Verifying the solution, well, people will talk about this, scoring functions. Initial R factors are high. There's log likelihood gain is a much better scoring tool. I won't go into refinement. Other people are going to talk about that. This is an important slide that Hugh prepared, knowing when to give up. I mean, Gideon Davis in York says, if you haven't solved your molecular placement by coffee, go back into the lab and make seleno met. And there's something in that. You can waste a lot of your life trying to solve a molecular placement solution when the model is not good enough, or you've got the wrong sequence. That's another reason. Anyway, it's going to be hard. If you have low resolution data and no decent model, it's hard. And the thing with automation is, of course, it allows you to test many, many molecules without having to sit there and scratch your own head. You're going to let the computer do the work for you. But there we are. Now, at this acknowledgement slides, these are photographs from Cuba, which Phil found for us. It's worth going on these workshops. It was such fun. And Ellie stayed up half the night drawing many of those figures, but anyway, it was good fun. And it was windy too. Hugh Jenkins gave a very nice talk, and I've nicked a lot of his slides he gave a talk at the BCA Summer School. Then there's other people whom I must acknowledge, Kevin, Keith, Johan, and so on. And I thought just a little bit of history. Those of you who are interested in history, the first, what now we didn't call molecular placement then, but was the beginning of molecular placement. Michael Rossmann and David Blow had two molecules in their asymmetric unit for chymotrypsin, so they wanted to see if they could, how well the molecules matched, whether they could have detected that from the diffraction observations, and in fact the self-rotation told them that yes, there were two molecules and how they were orientated. And the next example they wanted to try was insulin, because again it was known there'd be two molecules, and so we went on to do self-rotation functions on insulin, and insulin was a new challenge because the axes weren't perpendicular to each other, and boy, we made so many mistakes. But anyway, we did get to conventions. Then, over the years, of course, many people have made major contributions to pushing things forward. Tony Crowther was the person who first introduced spherical harmonics and changed the rotation function from something that took forever to something which was doable in real time. Jorge Navazao, I think, changed the whole way we looked at molecular placement and probably introduced the first pipeline for solving structures. Alexei Vargan wrote MOREP at the end of the 80s, and it's still maintained and used widely. The phaser team, which I've only put two of your photographs up because I can only find two on the web, Randy and Airlie, plus others, I should say. And that's, I think, is the end of what I need to say. Okay, so...